Example 4.11. A 100-ton closely wound circular coil of radius 10 centimeter carries a current of 3.2 ampere. A. What is the field at the center of the coil? B. What is the magnetic moment of this coil? The coil is placed in a vertical plane and is free to rotate about a horizontal axis which coincides with its diameter. A uniform magnetic field of 2 Tesla in the horizontal direction exists such that initially the axis of the coil is in the direction of the field. The coil rotates through an angle of 90 degrees under the influence of the magnetic field. C. What are the magnitudes of the torque on the coil in the initial and final position? D. What is the angular speed acquired by the coil when it is rotated by 90 degree? The moment of inertia of the coil, that is 0.1 kilogram meter square. Now see, number of turns in the coil, that is 100 given to you. Radius of the coil, that is 10 centimeter, so that is 0.1 meter. Current passed through it, that is 3.2 ampere. First, we want to calculate the field at the center of the coil. So we have the equation for the field at the center of the current carrying coil, that is mu 0 I upon 2R. If it have n number of turns, then we have to multiply by n. Substitute the values. N is 100, mu 0 4 pi into 10 raised to minus 7. Current I, that is 3.2, 2 into R, that is 0.1. Solve this one, you will get the answer. Then after, magnetic moment of the coil. Magnetic moment, that is I into A. If n number of turns are there, then multiply by n. So M equal to NIA. A, that is the area of the loop. So that is pi r square. So resultantly, the equation for the magnetic moment turns to Ni into pi r square. N, that is 100. I, that is 3.2. Pi 3.14. R 0.1 square. Solve it. You will get the magnetic moment of the coil. Clear up to this one? Now, the magnetic field given to you, that is 2 Tesla. So when any current carrying coil is placed in the magnetic field, the torque acts on it, and that is tau equal to mb sine theta magnitude wise. So initially theta, that is 0. So we can say initially the torque acts, that is tau equal to mb sine theta, that is sine 0, so 0. Finally, it is rotated by 90 degree. So in final position, tau, that is mb sine 90. Substitute the value of m here, which we calculated in the question B. Then B, that is given to you 2 Tesla sine 90, that is 1. So finally the torque, that is this much. Now the moment of inertia, that is given to you 0.1 kilogram meter square. Now torque tau, that is mb sine theta. See, here we have to calculate the angular speed gained by it when it is rotated by 90 degree. Now see, torque tau, that is equal to I alpha. I, that is moment of inertia, and alpha, that is angular acceleration. mb sine theta. Alpha, angular acceleration, that is d omega by dt. So I d omega by dt, that is mb sine theta. Now here d omega by dt, that we can rewrite as d omega by d theta into d theta by dt. But this d theta by dt, that is called angular speed, and d omega by d theta as it is. So now in this equation, replace this d omega by dt by omega into d omega by d theta. So we can write I into omega into d omega by d theta, that is equal to mb sine theta. So take this d theta on right hand side. So I omega d omega, that is equal to mb sine theta d theta. Now coil is rotated from 0 degree to 90 degree, and its angular speed, that suppose becomes from 0 to omega. So now integrate this equation on both the side. So on left hand side, the limits of the integration 0 to omega, and on right hand side, the limits of the integration 0 to 90. Now I for omega, the integration, that is omega square by 2, limits 0 to omega, so answer will be omega square by 2. On right hand side, mb, integration of sine theta, that is minus cos theta. So here if we substitute first upper limit, so minus cos 90, that is 0. Then minus cos 0, so that is 1. It implies that this bracketed part, that will be equal to 1. So finally we will get omega square, that is equal to 2mb upon I. So omega, that is equal to under root 2mb upon I. So under root 2m that we calculated in question B, substitute its value. B, that is given to you 2 Tesla. Moment of inertia, that is given to you 0.1. Solve this one. You will get omega this much radian per second. Clear to all of you? Now example 4.12. Question A. A current carrying circular loop lies on a smooth horizontal plane. Can a uniform magnetic field be set up in such a manner that the loop turns around itself? So answer will be no. Because for the rotation, torque required, and torque, that is IA cross B. So torque, that will be perpendicular to both A and B. Now, if your coil, that is like this in the horizontal plane, so area vector will be along the axis. Now, if perpendicular to area vector, torque is there, then torque will be in the plane of the coil. So here, if the torque is in the plane of the coil, then this will not be rotated like this around itself. Question B. A current carrying circular loop is located in a uniform external magnetic field. If the loop is free to turn, what is its orientation of stable equilibrium? So that in this orientation, the flux of the total field, external plus field produced by the loop, that is maximum 1. So stable equilibrium, that will be when torque is 0. So I A B sine theta. So angle theta, that is 0 between A and B. So suppose this one is coil, its area vector is like this, and the field, that is also in the direction of area vector. It implies that plane of the coil, that is perpendicular to the field, and the field of the coil itself, that is along the axis. So maximum flux will pass through this one. Now see, a loop of irregular shape carrying a current is located in an external magnetic field. If the wire is flexible, why does it change to circular loop? Because here on each infinitesimal small current element, if we consider the force acting, then that will be in the outward direction, and due to that, it will becomes the circular one. Or in other words, we can say the flux tends to maximize one, and if irregular shaped loop is there and it becomes circular one, then the flux passing through it, that will be maximum due to its maximum area. Clear to all of you? Now, circular current loop as a magnetic dipole. Okay. Say, we already derived the equation for the magnetic field on the axis of the circular loop of radius r carrying current I. That is B at x equal to mu 0 I r square upon 2 into r square plus x square raised to 3 by 2. Now for x is very much greater than r, we write B at x, that is mu 0 I r square upon 2x cube. Now here we want to represent it as a magnetic dipole. So equation of its magnetic field, if we represent in terms of magnetic moment, then we can say circular loop, that is as a magnetic dipole. So to introduce magnetic moment here, magnetic moment, that is I into A, area of the loop. So here multiply and divide by pi. So we can write mu 0 I into pi r square upon 2 pi into x cube. So B at x, that is mu 0. Now pi r square, that is area of the loop. So that is I into A upon 2 pi x cube, but I into A, that is the magnetic moment. So B at x, that is mu 0 m upon 2 pi x cube. Now rewrite this one. Here multiply and divide by 2 again. So we can resultantly write mu 0 upon 4 pi 2m upon x cube. Here see, the constant appears, that is mu 0 upon 4 pi. In case of electric dipole, we can write the equation of the electric field at any point on the axis of the dipole, that is E axis equal to 1 upon 4 pi epsilon 0 2p upon x cube. P, that is dipole moment, here m, that is dipole moment, and the constant in electrostatics, that is 1 upon 4 pi epsilon 0, and in magnetics it is mu 0 upon 4 pi. Okay, so if we consider the circular current loop as a magnetic dipole, then we can write the equation of the magnetic field at any point on the axis of it, that is this one. So from this analogy, now directly we can write the equation for the magnetic field at any point in the plane of the loop. Axis is perpendicular to the plane of the loop, and in the plane of the loop, so we can consider it as equatorial plane. Now see, in case of electric dipole, at any point on the equatorial plane, E equatorial plane, that is 1 upon 4 pi epsilon 0 p upon x cube. So from this analogy, directly we can write the equation for the magnetic field at any point in the plane of the loop. So that is mu 0 upon 4 pi. This constant is replaced by mu 0 upon 4 pi. Here electric dipole moment, here magnetic dipole moment upon x cube upon x cube. Clear to all of you? Now the magnetic dipole moment of revolving electron. See, when the electron is revolving around the nucleus, then the motion of that charged particle will constitute a current. So we can treat it as a current loop, and we discuss this thing. Any current loop produce the magnetic field. So here, if we consider the revolving electron as a current loop, then definitely it will produce the magnetic field at the center of it. And now We already discussed in the previous theory that current carrying loop, when produce the magnetic field at the center, then we can consider it as magnetic dipole. So we can calculate its magnetic dipole moment. Now see, suppose as shown in this figure, the electron is revolving in the orbit having radius equal to r with respect to the positively charged nucleus. Here, at any instant, the velocity of the electron that will be in the tangential direction. Now, first of all, we have to calculate the current constituted by this revolution of electron. So, for revolving electron, if we consider any point, then we can say this thing, the amount of charge passing through that particular point when one revolution of electron is completed, then that is equal to E. Now, current I, that is Q by T. So as per that, we can write the amount of charge flowing, that is E, and time taken to complete one revolution, that is capital T. Now, electron is revolving with a speed V in the orbit having radius equal to R. So when one revolution is completed, the distance covered, that is equal to the circumference of the orbit, 2 pi r. So we can write the time taken by electron to complete one revolution, that is its period, equal to 2 pi r by v. Now here in this equation, if we replace this capital T by 2 pi r by v, then resultantly we will get the equation of the current constituted by this revolving electron, that is EV upon 2 pi r. Clear up to this one? Now, magnetic moment, M, that is I into A. So A, that is the area of the orbit, that is pi r square. Now substitute the equation of I which we derived earlier. So that is EV upon 2 pi r into pi r square. So pi cancelled, 1 r will be cancelled. So magnetic moment, that is of EVR. Okay. Now here multiply and divide by mass of electron. So we can write M, that is equal to E upon 2me into MEVR. But in standard 11th, we studied this thing. Angular momentum L, that is MVR. So we can replace this MEVR as angular momentum of the electron. So magnetic moment, that is E upon 2me into L. L, that is the angular momentum. So here in the vector form, we can write vector M, that is equal to minus E upon 2me vector L. Why here we introduce negative sign? Because if we find out the direction of the magnetic moment and the direction of angular momentum, then both are mutually opposite. And therefore here we have to introduce this negative sign. Now, M by L, that is equal to E upon 2me. If we substitute here the value of E, 1.6 into 10 raised to minus 19, and mass of electron, that is 9.1 into 10 raised to minus 31 kilogram, then we will get this particular ratio, that is 8.8 into 10 raised to 10 coulomb per kilogram. And that is called gyromagnetic ratio for electron. Clear up to this one? Now see, M, that is equal to E upon 2me into L. This is orbital magnetic moment. Now L, the angular momentum, that is equal to nh upon 2 pi as per Bohr's hypothesis. So at present, just you remember this thing. Later on in the chapter of atoms, we will discuss this thing in detail. At present, just you have to remember this thing. The angular momentum of the electron in orbit, that will be in the integer multiple of h upon 2 pi. So we can write that is nh upon 2 pi, where h, that is Planck's constant, its value, that is 6.626 into 10 raised to minus 34 joule second. Now substitute this value of L here. So m, that is equal to E upon 2me into nh upon 2 pi. Now see here. In this equation, if we take n equal to 1, then we can write m, that is equal to E upon 2me into h upon 2 pi. Now substitute the values. E, that is 1.6 into 10 raised to minus 19. H, that is 6.626 into 10 raised to minus 34. 2 into these two, 4. Pi, that is 3.14. Me, that is 9.1 into 10 raised to minus 31. So finally you will get the orbital magnetic moment, and that is for ground state, because here n equal to 1. And in chemistry you studied this thing, this n is called orbital quantum number. So your answer will come to 9.27 into 10 raised to minus 24 ampere meter square. And this is called Bohr magneton. This is called Bohr magneton. So Bohr magneton, that is nothing but the orbital magnetic moment of the electron in ground state. Clear to all of you? The next topic, that is the moving coil galvanometer. Galvanometer is the device with the help of which one can detect or measure very small amount of current. This one is the galvanometer which we use in laboratory. Okay. Now this one is the schematic diagram for its construction. Okay. So in moving coil galvanometer, we can say the principle on which it works, that is the torque acting on the current carrying coil when it is placed in the uniform magnetic field. On that principle this works. Clear? We already studied in the theory, when any current carrying coil is placed in the magnetic field, the torque acts on it, and due to that it will be rotated. Now see here, in the construction of this one, two cylindrical type magnetic poles north south are there. So due to this type of shape of the magnetic poles, the magnetic field, that will be a radial one. Okay. Now in this particular magnetic field, a coil is placed. See, this one is the rectangular coil placed in the magnetic field. So here the plane of the coil is in the plane of the uniform magnetic field. So we can say the area vector for the coil, that will be perpendicular to the magnetic field. Then here, for this particular coil, one axis is attached with this one, and then it is pivoted from upper and lower side. So with respect to these two support, it can rotate like this. Okay. Now, when the current is passed through this one, the torque will act on it. So this will be rotated in this way. But now here, with this axis of it, a spiral spring is attached. So when this one is rotated like this, the torsion will be produced in the spring. So spring will produce the restoring torque. So when the torque acting on the coil and the restoring torque produced in the spring both becomes equal, then your coil will be steady. Now, one pointer is attached with the coil. So as coil rotates, that pointer will be also rotated. It will show you the deflection. So when the coil becomes steady, this pointer will be steady on the scale. Now, initially, by giving known currents to this galvanometer, the scale is already calibrated. So with the help of this steady pointer, you can measure that particular very small current, or due to deflection of this one, you can say yes, the current is there in the circuit, so we can detect the presence of current. Clear to all of you? Now, torque acting on the current carrying coil placed in the uniform magnetic field that is given by the equation NIAB sine theta. But here the area vector and the magnetic field are perpendicular to each other. So theta, that is 90. So sine theta, that is sine 90, that is equal to 1. Now, in this particular case, the torque acting on the coil, that becomes maximum one. So we can say here tau maximum acting on the coil, that is NIAB. Now, when torque acting on the coil and restoring torque due to spring becomes equal, then coil will be steady. So we can write the restoring torque, that is K into phi, that is NIAB, where K, that is known as torsional constant. Torsional constant of the spring means restoring torque produced per unit deflection. Phi, that is the deflection. So per unit deflection, whatever the restoring torque is generated, that is called its torsional constant. So from this equation, we can write phi, that is equal to NAB upon K into I. Torsional constant, that is the constant for the given spring. N, that is number of turns, constant one for the given coil. Area of the coil constant. B, that is uniform one, so constant. So here we can say phi, the deflection, that proportional to current I. So if more current is passed through the coil, more deflection will be obtained on the scale. If less current is passed, then less deflection will be there. Clear to all of you? Now, deflection per unit current passed through the coil, that is called its current sensitivity. So we can write the equation for the current sensitivity of the galvanometer. So that is I S equal to phi upon I. That is nothing but the deflection per unit current passed through the coil. And we can write that is NAB upon K. So from this one, you can write the equation for voltage sensitivity also. Say, here on both the side multiply by 1 upon R. So phi upon IR, IR, that is voltage. So phi by V, so that is nothing but the deflection per unit potential difference. So that is NAB upon KR, and that is called voltage sensitivity of galvanometer. Clear to all of you? Now the next topic, that is galvanometer as an ammeter. Ammeter, that is the device which measure the current flowing through any branch of the circuit. Okay. Now see, we already discussed this thing in previous theory. Galvanometer that measure the current, that detect the current. Then why we think about the ammeter? Because galvanometer, that is very sensitive device. With the help of galvanometer, you can detect or measure the current which one is very small, of the order of microampere. So here directly we can't use galvanometer as a current measuring device, means ammeter. Why? Some limitations are there. So let's discuss these limitations. Okay. See, suppose we have the circuit as shown in the figure, in which the resistance is connected with the battery having V volt. So if we connect this circuit, then how much current will flow through resistance R? So as per Ohm's law, we know this thing. The current I, which is equal to V by R, that much current will flow through this resistor. And now we want to measure this particular current flowing through the resistance R. Now, any device which can measure the current, where we have to connect it. So we know this thing. In series combination of components, the current through each component will be same one. So if we connect the current measuring device, say galvanometer, directly with the resistance in series. But here what happens, as soon as we connect the galvanometer in series with resistance. Now see here, this is galvanometer. Galvanometer itself have some own resistance. So to understand it, here the resistance of the galvanometer is represented with this galvanometer by Rg. So now the total resistance of the circuit itself is changed. So now current flowing in the circuit, that will be changed one. And now your current, that is I dash equal to V upon R plus Rg. Actually, you want to measure the current I flowing through the resistance R. And as soon as you use galvanometer to measure this current, the current itself in the circuit is changed. This one is one limitation. Second thing, galvanometer is very sensitive device and its current capacity, that is very less. So if slightly large current, then its current capacity pass through it, it will be permanently damaged. So these two limitations are there, due to which we can't use galvanometer as an ammeter. Now what we have to do to convert this galvanometer into ammeter? Up to this one. Now see, if you connect this galvanometer in series with resistance R, then the current in the circuit itself is changed. Now suppose you want to keep this current I dash equal to I, then from this equation mathematically you can understand this thing what to do. If you want to make this I dash equal to I, means simply you can say you have to make Rg equal to 0. If you take Rg equal to 0, then I dash equal to I. But practically it is not possible to make Rg equal to 0, because if you have galvanometer, definitely it will have some resistance. Then make it as possible as a small one. Now see, suppose R is very much greater than Rg, then R plus Rg, that will be nearly equal to R. So in that case, I dash, that will be equal to I. It implies that you have to make the resistance of galvanometer that is very small. Now we know this thing. In parallel combination of resistances, the resultant resistance that will be smaller than the smallest one connected in combination. આવું આપણે આગળ ભણી ગયા છીએ. So if you want to make the resistance of the galvanometer very small, then very simple thing, connect very small resistance parallel to the galvanometer. And the small resistance connected parallel to the galvanometer to convert it in ammeter, that is called shunt. That is called shunt. So now the resultant resistance that will be greater than this RS, smaller than this RS. Now see, suppose the circuit current is I. So now when this current reaches at this point A, it will be divided in two parts. Now this particular resistance is very small compared to resistance of the galvanometer. So majority current will pass through this one. And through the galvanometer, only the current equal to its current capacity will flow. Suppose here, through the galvanometer current flowing, that is Ig, that is its current capacity, and remaining current flowing through shunt, say it is Is. Now, for this closed loop ABCDA, apply Kirchhoff's second rule. So A to B in the direction of the current, so minus Ig into Rg. Then B to C to D. So here Is, that is D to C, you are moving C to D. So in the opposite direction of current, you can write the potential difference positive. So plus Is Rs, that is equal to 0. So you can write Is Rs, that is equal to Ig Rg. Therefore, Rs equal to Ig upon Is into Rg. But total current was Ig flows through the galvanometer. So this Is, that is I minus Ig. So replace this Is by I minus Ig. So we can write Rs, that is equal to Ig Rg upon I minus Ig. So this is the equation for the shunt, which should be connected parallel to the galvanometer to convert it in ammeter. See how one can use this equation. So see, suppose galvanometer is given to you. For that given galvanometer, suppose its current capacity, that is 1 milliampere. Then its own resistance is suppose 25. So here substitute Ig, that is 1 milliampere, means 10 raised to minus 3 ampere, Rg 25 ohm. Now you want to convert this galvanometer into ammeter, which can measure 10 ampere current. So I, that is 10 ampere, Ig 10 raised to minus 3. Solve this equation, calculate Rs. Then after, connect that much resistance parallel to the galvanometer. Then after, by passing known currents through the galvanometer, recalibrate its scale. Now you can use it as an ammeter, which can measure maximum 10 ampere current. Clear up to this one? Now next topic, that is galvanometer as voltmeter. See, directly again we can't use galvanometer as a voltmeter. Voltmeter, that is the voltage, or we can say the potential difference measuring device. So see here the limitations. Suppose through resistance R the current I is flowing, value of I that is V by R. So the potential difference between two terminal of R that we can write IR and this voltage IR that we want to measure. So any voltage measuring device that always will be connected parallel to the component, because in parallel combination the voltage is same across each component. Now suppose here we connect galvanometer directly parallel to this resistance. So first thing, current itself will be changed, because initially the circuit resistance was R and now the circuit resistance, that is the parallel combination of R and Rg. So current will be V upon RRG upon R plus Rg. Now current is changed. Again, that particular current when reaches here, it will be divided in two parts. If resistance R is greater than Rg, then majority current will pass through the galvanometer. It will be damaged. Now first understand mathematically. If you want to keep your current equal to V by R, then see, concentrate here. If we take Rg that is very much greater than R, so if we take Rg very much greater than R, then this Rg plus R that you can write simply equal to Rg. So in this equation, RRG upon R plus Rg, this R plus Rg that is nearly equal to Rg. So Rg cancelled and your resultant resistance that comes to R. Clear up to this one? So now here mathematically we discussed Rg that we have to take very much large. Now we know this thing in series combination, the resistance will be sum up. So to make the resistance of the galvanometer too much large, very simple thing, connect large resistance in series with it. So here the potential difference across galvanometer that will be equal to potential difference across R, and that is equal to V, this one. So we can say here between these two terminal of the galvanometer, if the potential difference is V volt, then we can write V equal to current into total resistance. So Ig into total resistance, that is Rg plus Rs. Therefore, Rg plus Rs equal to V by Ig. Therefore, Rs equal to V upon Ig minus Rg. So, this much series resistance that you have to connect with galvanometer to convert it in voltmeter. Up to this one clear? Now, how one can use this one? Suppose galvanometer is given to you. So for that galvanometer, current capacity and its resistance will be given to you. Suppose current capacity is 1 milliampere and its resistance is 25 ohm. Now you want to convert that galvanometer into voltmeter, which can measure maximum 10 volt. Then here you have to substitute V equal to 10. Then solve this equation. You will get value of Rs. Now take that much resistance and connect it in series with galvanometer. Then after, first apply known potential differences and then recalibrate the scale of the galvanometer. And now you can use that one as a voltmeter which can measure maximum 10 volt. Clear to all of you? See, to convert galvanometer into ammeter, theoretically we discussed this thing, the resistance of the galvanometer, that should be 0. But practically it is not possible. So remember this thing, keep this thing in your mind. For ideal ammeter, the word used ideal ammeter, the resistance that should be equal to 0. And here, to convert galvanometer into voltmeter, its resistance that should be as possible as large one. So we can say for ideal voltmeter, resistance should be infinite. Clear to all of you? Now example 4.13. In the circuit, the current is to be measured. What is the value of the current if the ammeter shown? A is a galvanometer with resistance Rg equal to 60 ohm. B is a galvanometer described in A but converted to an ammeter by the shunt resistance Rs equal to 0.02 ohm. Is an ideal ammeter with zero resistance. So first we have to consider the resistance of this, that is 60, and what is the current that we have to calculate. Then after this galvanometer is converted into ammeter by this much shunt. So what is the resistance of this one that we have to calculate? So this Rg and Rs are parallel. So what is the resultant resistance that we have to calculate? And then after according to it, we have to calculate the current. Then ideal ammeter means its resistance is 0. So at that time, what is the current in the circuit that we have to calculate? Now see, this is our circuit. So when resistance of the galvanometer is a 60 ohm, so here resistance 3 ohm that is already in the circuit. So with that in series, resistance of this one is 60. So I, that is V upon R plus Rg. So 3 upon 3 plus 60. So 3 by 63. This much current will flow in the circuit. Then galvanometer is converted into ammeter by shunt resistance Rs equal to 0.02. So now the effective resistance of the entire circuit. So this is R, and with this R, the series, that is Rg Rs upon Rg plus Rs, because shunt is always connected parallel to galvanometer. So here Rs, that is very much small compared to Rg. So here in denominator, if we neglect Rs, then Rg cancelled. So this is nearly equal to R plus Rs. So 3 plus 0.02, resultant resistance of the entire circuit, that is 3.02 ohm. So now the current I dash equal to V upon R plus Rs, that is 3 upon 3.02. Calculate it, you will get the answer. In third case, ideal ammeter, that is with zero resistance. So if resistance of this current measuring device is 0, then resistance in the circuit, that is only 3 ohm. So I, that is V by R. So that is 3 by 3. So in that case, the current in the circuit will be 1 ampere only. Clear to all of you? So chapter is complete.